All right, Chapter 5, Probability Distributions. This is a longer section, so I'm going to go along at a good clip here. Hopefully you don't have to pause the video too often. Key ideas. What are the necessary requirements for doing probability distributions? Included in that is obviously definitions, unfortunately. And then we'll also be calculating both mu and omega. These are obviously the mean and the standard deviation. And then we use that to determine whether a particular statistic is significantly high or low. All right? All right. First of all, we define a random variable. Typically, it's called x, and it's determined by chance. More on that as we move through. But every probability distribution that you encounter has to have this random variable in it. Okay? What does a probability distribution look like? Well, it can come to us in three different ways, either a table, a graph, or a formula. And you need to be able to use all three of them. There are formulas that spin off of distributions as well. And it shows the probability for each value of the variable. More on that in just a moment. Again, that would be the value of the random variable. This variable that we use must be numerical. So if, for example, heads and tails, eye color, these kinds of things, we can't unless we convert them into a number. The problem with converting them into numbers is that then you have to interpret what is a 1.6, for example. How do I read that as an eye color or a heads or tails? Another requirement of a probability distribution is that the sum, okay, of the probabilities has to be 1, aka 100%. Now, this is a little flag that tells us we are now working with populations, not samples. Sometimes when you add those percentages up, you get something like 0.99 or 1.001. That isn't an error, except for the fact that it might be a rounding error in the problem, which caused us to get close to 1. But in theory, it should be 100%. Each probability must be between 0 and 1. All right, discrete random variables. So these variables that we use are sometimes finite and countable. This should be something which you've seen before in algebra class, college algebra class. And then continuous random variables, where they are an infinite or uncountable collection of values. So they'll ask you to kind of, note of that as you go through an example. And we can have both. Doesn't matter in probability distributions. So here we go, an example. Number of tails when 3 coins are tossed. Now notice how this is phrased, the number of tails. So in this case, my numerical value isn't the tail, but how many, right? So x is how many tails do we get in 3 tosses? And you could have, obviously, 0, 1, 2, or 3. Here is the sample space that helps me build my probability table. Yeah, there is, for example, only one case where there are no tails, and that would be that one, right? And there's one case when there are 3 tails. And then we can look at both 1s and 2s, and there are 3 of those, so 1 out of 8 and 3 out of 8 are the 2 values that show up in my probability. So this is called a probability distribution of tails in 3 tosses. So that's the table version. All right. It is discrete, as we can see. There are 4 possible values. And the sum, you can see, is 1. You could verify that on your calculator. All right. So here now is a graph of a same thing, but of the probability histogram. Now this should be reminded because it looks like a frequency table, but it uses probabilities instead of relative frequency. All right. The width of each of these bars also is just 1. So the area of each of them is equal to the probability. So for example, what is the probability of getting a 2 that is 2 tails? So I take 1 times my height of 0.375. So that area, sorry, did I say 2? 1, yeah, 1 times 0.375 gives me my probability. That's a really important idea in going into calculus. End of this study. We're not going to go there, don't worry. Some bad news. When I started out writing these notes, I did it for 3 coin tosses because I wanted to be different than what the textbook was doing. And then I came to this section and I couldn't figure out how to do a probability formula for 3 coin tosses. I did a little research. I couldn't come up with it. So for now, this probability formula, which generates this, only works for 2 coin tosses. Somehow I have to change this. And I tried monkeying around with it, but I couldn't figure it out. So here we can see the probability of getting 2 heads or tails, doesn't really matter, in a 2 coin toss is 25% chance. 1 out of 4. A new notation that is going to be coming up is 0 plus. And it just means that our value, our probability in particular, is really close to 0. And it's very negligible distance away. We don't want to round it to 0 and say that the probability is 0 because that would be incorrect interpretation. But 0 plus just means you are really, really close, okay? Beyond our rounding values, so to speak. All right, here is an example of a bad probability distribution. All right, first of all, notice X is not an countable, right? These are not items which are numerical. So that's a problem. And then finally, another reason, if like that wasn't enough, if I add these up, I get 1.57. I don't get 1. So the summation is 1.57, which is not 100%. And they'll ask you to notice that in the problems. All right, here's some formulas now. Hurrah. Notice these formulas are not called statistics, but parameters. And that's because the population is not a sample, meaning I don't take a few of them, I take all of them and analyze them. So to get the mean, we sum the multiplications of each of those X random variable times the probability, and then add that up, all of them. And that gets me what we would think of maybe in the past as a weighted mean. Then to get the variance, we have 2 formulas. And from these formulas, we can calculate the standard deviation because it's pretty simple to go from the variance to the standard deviation. We just take a square root. This one is easier to understand what's going on. I take the mean subtracted from each data item, and I square that and multiply it times its corresponding probability. But if I had to calculate it, this is the route that I would go to. This is probably a shorter route. Okay? I square each data item multiplied by the probability, and then I subtract from that the mu squared. Now notice this is the sum right? So this parentheses is closed here. I add all those up, and then I subtract once. So it's easier to do there, but it's harder to understand what's going on in the problem, which is kind of important. So I'm going to be doing a problem involving that method. Okay? Rounding rule. Just like in the past, we use one more decimal value than that is given to us in the random variable. Except when you are very close to a maximum or minimum value. I kind of already talked about this, but if I'm really close to 0, right, the hydraulics failure on a airplane, remember with 4 hydraulic independent engines, was obviously this has not been rounded, right? And to round it to the nearest tenth would be 0, and that would be incorrect. You don't want to say that the probability of failure is 0, because it's not. It's negligible, but it's there, and we must be aware of that value. And then, how do we get what's known as the expected value? And note here, this expected value can be thought of as the mean of the outcomes. So the expected value, which is going to be used capital E, is done by adding up. Notice that formula is the same as our formula here. Okay, but we call it the expected value. And the reason is that if you conduct this trial many, many, many times, right? Indefinitely is what we would say. Then this is what we would expect to happen. It doesn't need to be a whole number. For example, what is the expected value of a boy in 5 births is 2.5, which technically is impossible. And yet we use it to interpret results, okay? All right, looking at an example here, calculating the mean and the standard deviation of a data set. Going back to our number of tails or heads, I forget what we were doing here. Doesn't really matter which one it is because it's the same, for 3 coin tosses. So I take each of these, multiply them together, right? And then I add these up and get the mean, okay, mu. Then over here to calculate my variance, I take each x item, random variable, x minus my mean, square that result, multiply it times the probability, and that gives me 0.28125. Add these all up, and that gives me what we would call as my variance. Again, to go here, we take a square root, and that gives me my standard deviation, 0.9. So summarizing, interpreting, the mean of tails of 3 tails, I think is what we were doing, is 1.5. Okay, and 3 coin tosses. The variance, sorry, not the mean of 3 tails, the mean of 3 tosses is 1.5. And in this case, we were looking for tails, correct? Or heads, it doesn't matter which one you're looking for. The variance is 0.8. All right, and the standard deviation is 0.9. Notice how I rounded each of those to the nearest tenth, because they didn't give me any other directions, so that's what I'm going to use. The expected value, the expected value from 3 tosses, again. And again, we're looking for tails, is 1.5. All right. Finally, what makes a particular value significant? And so we're trying to make sense of particular data items that are given to us. All right. First of all, we have a range rule of thumb, and then later on we have what we would call significantly high and significantly low probabilities. These should be somewhat familiar to us because we've seen this before. First off, range rule of thumb. This is a guideline, and the guideline here is something the textbook uses that were plus or minus 2 standard deviations away. So if I take the mean minus the standard deviation, 2 of them, and add on 2 of them, that gives me the regions where values are significant. The ones in the middle are not significant. They're expected. They should happen. The majority of our data values live there. So an example would be, is 3 a significant number of tails in our 3 coin tosses? So we have our mean of 1.5. We have our standard deviation. So I take my mean, I add, in this case, because I'm above, 3 is above 1.5. So I add 2 of them, and I get 3.3. So 3 is not significant because obviously 3 is less than 3.33, which was 2 standard deviations above. All right. Another way to look at it is not at the standard deviation, but just look at the probability of that or more. Now that phrase is kind of important. You don't want to just say the probability of X. So we would say things like the probabilities of 3 or more tails in 3 coin tosses, which is kind of silly to say because you can't really have more than 3. Okay? But we can when we have more trials, obviously. Or 3 or less. And if that probability is less than, in both cases, 0.05, then you're either significantly high or significantly low. All right? So straight up looking at the probabilities instead of their standard deviations. Now, this is kind of an important rule because statisticians use this type of rule when we look at claims or data items, all right? So if you're under an assumption that P of X is very small and the outcome occurs significantly less than or greater than what we expect, okay? So we're either under, one of these two or we're over here, right? Then we conclude that the assumption is incorrect. And the assumption would be something like, okay, 3, you can expect to get 3 in a coin toss. Well, in this case, you can, because obviously 3 tails was not exceptional. But if we came out with a scenario where it wasn't, then we would say it's not. Like this next example here. The book started off this example with the NFL and doing coin tosses at the end of the game to determine who does overtime. And they found out that 252 times the winner of the coin toss won the game. And so the question is 252 out of 400 significant? Right? Is there a significant advantage to winning the coin toss? And what they found out was that, sure enough, okay, the probability of this.
Attention students.
Oh, hello.
Joseph Whitman, please report to the student office. Joseph Whitman.
So the probability is approximately a little bit more than 2%, which is definitely less than our threshold of 5%. So 252 is significantly high. Again, as we might expect, the mean is 230 out of 460, right? The middle. And our probability distribution will look like, that with 400 tosses, 460 tosses. Okay? And so that clearly is a sign that we shouldn't be using coin tosses to determine who goes next. Or we have to somehow balance the game, that the coin toss doesn't affect it that much. All right. Probability of at least, not exactly. And when we say the probability of like 502 heads, that probability in the 900 heads out of 1,000 tosses, the probabilities of those are identical. All right? So we're usually focusing on 502 or more, 900 or more, right? This one, 900 or more out of 1,000, is like super close to 0. okay? Very low. This one, that's only 46, that's 46% of the chance. That is not low, okay? So make sure that we are aware of this phrase at least, okay? So they're going to say or more. We close with an example of betting an expected value. So I should have highlighted my example. Which bet is safer? So here is the problem. All right, and we turn to gambling. You can look at gambling and insurance both under the same light. They're very easy to analyze because the numbers are kind of firm. Gambling is even more so because you can do theory on the rolling the die, whereas having an accident or getting sick from a disease kind of has a little fudge factor in it. All right, so we look at which bet is safer, the roulette wheel or craps. And the roulette wheel has a $5 bet. Craps also has a $5 bet. The payoff of roulette is $175, which is kind of glamorous, right? Who doesn't want to win $175? Whereas craps, you only win $5, more than what you bet, okay? So you actually win 10, but you bet 5, so overall you win 5. And likewise here, you win 180, but because you bet 5, you only win 175. So here's our probability of losing, 37 out of 38, pretty good chance, yeah? Probability of winning, not very much. And here we can see that our probabilities in this case are much closer to that halfway threshold. So we do a little bit of math and see what these turn out. So we take our bet, that's our money out, times the probability, plus the money in times the probability of winning that, gives us a expected value. Meaning if we played this game 1,000 times, okay, we would lose every time 26 cents. And then we do the same thing here with our craps game and look at the 5 and the 5, and that shows us losing 7 cents every game. So clearly, if you're there for the long haul and you want your money to last, playing craps less likely to lose a lot of money at once. All right? Phew. Okay, you made it through, kids. Have at the homework.